Okay, so let's continue with this example, and I zoomed out a little bit. So what I want to do next is I want to stylize, or I want to come up with some functions that represent those stylized behaviors. So for the total utility function, an example would be total utility equals 16 times the square root of x. And the square root of x, that could also be written, if you want to, if you prefer it this way, like 16 times x raised to the 1/2, not negative 1/2, 1/2. So negative raised to the negative 1/2. So that would be the same. And just to review quickly, sometimes you may see, as I just did accidentally, a negative sign here. So for example, if you have x raised to the negative 1, that also can be written as 1 over x. Or likewise, if you have x to the negative 2, that would be equal to 1 over x squared. Or if you have x raised to the negative 1/2, that would be the same as 1 over x to the negative 1/2, or 1 over the square root of x. And last but not least, if you have something raised to the 0, x raised to the 0, that is 1. And even if you have like 1,000 raised to the 0, that is also 1. Okay, so make sure that this is clear, because that may come in handy in some of those applications. Okay, so now let's erase this again. And so, okay. So here for the S-shaped production function, we have an example which is x, so output is equal to, I have it here, I need to look it up somewhere, okay, so minus 0.05 times L cubed plus 0.75 times L squared plus 0.2 times L. Okay, so a function like this, a cubic function, will give you something like the S-shaped curve. And for the total cost function, we may have something that is given by 0.05 x cubed minus 0.75 x squared x squared plus 4x plus 5. Okay, so here this plus 5, that would be the fixed cost, because even if you have no output, you plug in for x0, you still have cost of 5, so that must be the fixed cost. But the point at this here is now that those three functions represent the first, the graphs in the in the first row. So those are examples. So now in order to get to the graphs on the second row, we have to take the derivative, the first derivative. So we have to take the total utility function and derive it with respect to x. So that is written as we want to know the change in total utility when x changes a little bit. So that is the mathematical writing for the first derivative of the total utility function. Okay, so now the derivative rules are that whenever you see an exponent, the exponent goes in front. So here we see an exponent of 1/2. So that means that one goes in front of the function. So we have now 1/2 times 16 times x raised to the 1/2. So that is the first step. We take the exponent, bring it down, but then in a second step we have to subtract from the exponent -1. I don't know why that is. Somebody much smarter than I am figured that out, but this is just the rule. So in the second step we have to subtract here -1. Okay, so now we can simplify a little bit. So this gives us now 1/2 times 16, well that's 8. Okay, so this is gone, and then we still have x raised to the 1/2 minus 1, that is x raised to the -1/2. -1/2. And as I showed you earlier, if something is raised to something negative, we can also write a 1 over that term, so we get 8 over x raised to the 1/2, or I start a new row, 8 over the square root of x. Okay, so that was the first example. Now let's take the derivative of the production function and derive the marginal product. So now in this case we will say we have the change in output dx relative to the change in input, which is labor, because here we have labor to the right side of the equation. And then we do again the same thing. So the exponent of this term goes in front. Okay, so now we have 3 times -0.05 times L raised to the 3. But now we have to subtract again here -1 again, so 3 minus 1. Okay, so now we move to the next term, plus, again the exponent of L goes in front, so plus 2 times 0.75 times L raised to the 2 minus 1. That's always the second step. You must not forget to subtract 1. And then here for the third term plus 0.2 times L, there's basically an invisible 1 up there. So the 1 goes in front, the invisible 1, so plus 1 times 0.2 times L raised to the 1. But now we have to subtract the 1, so 1 minus 1. So this term becomes 0. Okay, so now we can simplify. So now we get 3 times -0.05, so that is -0.15 times L squared, because 3 minus 1 is 2, plus 2 times 0.75, that's 1.5, times L raised to the 1, so we just can write times L, and then 1 times 0.2 times L, so this last term is 1, so we just get plus 0.2. 1 times 0.2 plus 0.2. Okay, so now let's move to the next one. Let's see if I should. Okay, so now we take the derivative of the total cost function and we derive the marginal cost function. So that is the change in total cost with respect to the output. That's the marginal cost. Okay, and now the 3 goes in front. So 3 times 0.05 times x cubed minus 1, then minus 2 times 0.75 times x squared minus 1 plus 4x, so plus, there's a 1, the invisible 1 again, so 1 times 4, so 4 times x, but then we have 1 minus 1, so that's a 0, and the 5 doesn't have an x, so there's nothing we can derive, so that becomes a 0. Okay, so now we can collect terms again. 3 times 0.05, that's 0.15 x squared minus 2 times 0.75, so that's minus 1.5x, and then 2 minus 1, that's just a 1, so that's an invisible 1, and then plus 4x, but the x raised to the 0 is 1, so we are just left with a 4. And that's it. So these are our results. And what we do in the next step is, I want to show you in Excel that those functions here that we just derived give you what we see in the second row of the graphs that I sketched. But I do that in the next video.